So we're here for lecture 12 on the proof complexity as a computational lens course. We're leaving polynomial calculus degree behind, almost. But we are going to talk a little bit about width in resolution mainly and degree in polynomial calculus. Most of the proofs today are going to be for width. Everything pretty much holds for degree also. So as you've seen so far, width is somehow a crucial measure for resolution proofs. And this was observed early on, apparently already by Galesi in 1977. And since then we have learned, so throughout today, unless stated otherwise, F is a KCNF formula. I'll tend to think of K as a constant. Any n, lowercase m floating around is the number of variables, just for concreteness. So we've seen it's sort of obvious that if the width is bounded by W, then the resolution length or size, it's the same for resolution, we count number of clauses, is essentially n to the W. That's an easy upper bound. For tree-like resolution, we had a very tight lower bound, which says that the size or the length is exponential in the width. For general resolution, we got a slightly less nice bound that said that the length is exponential in width squared divided by the number of variables. And then we haven't talked about space, so we're getting a little bit ahead of ourselves. But if you look at the memory you need for a self-contained presentation of a proof, then it's natural to count the same thing as size counts. So usually the space measure for resolution is number of clauses. For polynomial calculus, we will count the number of monomials. Then we know for resolution that the space is also lower bounded by the width. And in fact, I think we will see in this course that if you count total space, which is you look at the sum of all literals in all clauses, counted with repetitions, then that is width squared. So width is somehow a central measure to understand lots of things in resolution. And now it's interesting to understand how tight these bounds are. For instance, this is a stupid, for resolution, this is an immensely naive counting argument. This is really tight. We like this bound for tree-like resolution much better than this one for general resolution. Can we improve 3 to get closer to something like 2, say? From this, you can see that, well, if the space is small, then the width is going to be small. Does the opposite hold, so that somehow space and width are measuring the same thing? And one more technical question is that the way we proved 3 was actually we took a short resolution refutation and then massaged it to get a somewhat narrow refutation. Unfortunately, in this process, the length, the size of the refutation blew up exponentially. Is that necessary? Those are the kind of questions that we could ask. So today we're going to talk about whether this is tight and whether this can be improved. And note that you could ask, okay, so I'm going to focus on resolution, but let me just say for polynomial calculus, you have sort of the same questions. Let's just think of substitute width by degree and length, of course, then we're thinking about space. And we know that there's an analog of 1, so low degree implies somewhat small size, though the argument is a bit more complicated. We don't have any analog of 2 to the best of my knowledge for tree-like polynomial calculus. I don't know if people have thought about this or if it is known, but it just seems to me like a nice question. We do have exactly the same kind of lower bound on size in terms of degree due to Impagliazzo, Pudlák, and Sgall. Again, we can ask if it can be improved. Interestingly, for monomial space, which is the measure you have in polynomial calculus, 4 is strongly believed, I think, to be true. Reasonably strongly believed to be true, but this is open, and I don't know if anything is known about 5. So this is bringing us again to nice open questions that might be approachable once you listen to a few lectures on this course. So, but today we're going to talk on 1 and 3. So the spoiler alert is we'll see that this is tight, and this is to some extent also tight. And I'm going to focus on resolution, but with minor modifications, you'll get the same thing also for polynomial calculus. So just as a technical warm-up, so for any, I want F to be a KCNF formula or 3CNF formula ideally, but many formulas aren't, pigeonhole principle formulas, for instance. Then there's a standard translation into CNF. So I'm going to use the notation that whenever I have a CNF formula F tilde is the formula converted to 3CNF. Okay, and what does this mean? Well, suppose I have a clause that is a bunch of literals. The width is W. If W is at most 3, then I don't need to do anything. So then C tilde is itself. And otherwise, and now I'll do something slightly differently from what I did like a few lectures back, I think. It doesn't really matter. But I'm going to introduce a bunch of new fresh variables, AI, that are local to this clause. So I could tag them by C also if I like, I guess. And then I just write this 3CNF formula that looks something like this. And I think the pattern is clear, and then you have to think about the indices. I think you're going to get all the way up to A W minus 2, and then the final two literals LW minus 1 or LW. So I'll just let C tilde be this CNF formula. And now if F is a CNF formula consisting of M clauses, then F tilde is just obviously the conjunction of all the tildes. Okay? And now it's kind of obvious, so I won't maybe even write it down, we have it in the notes, that, okay, so let me write it informally, that the size in resolution or polynomial calculus or, well, almost any reasonable proof system is big O of refuting the original formula. And also for width or degree of refuting F tilde, it's the same. It's actually less than equal the width degree of refuting it. And this is not so hard to see. I mean, once you're given C tilde by a few resolution steps, you just recover C, and then whatever proof you had over here, you just run it. And now, why do I pick up a big O there? Well, because I need to reconstruct the formula, so let's play it safe. What about width degree? Well, then you realize that the reconstruction actually doesn't increase anything. Yeah? So therefore, but interestingly, note that this is only one way. So an interesting question, and this is maybe something that would be nice to formalize at some point. I'm improvising a little bit now, but so I'll be not very precise. But for many formulas and many complexity measures and many proof systems, we actually have more or less an equivalence. But taking a lower bound for F and getting a lower bound for F tilde is not automatic, because note that F tilde is, strictly speaking, a stronger formula. And so you always need some hacks to sort of take an F bound and patch it to get an F tilde lower bound. And this usually works, except we'll see when we get to space that there, for some reason, when you go to algebraic proof systems, it doesn't. And we don't, even when it does work, like mostly for resolution space and for resolution size, for width, it's like you have to do things. And it would be nice to see if we could maybe, I don't know, if you could say something general when this works or not, which some kind of general statements. Another thing that will be convenient is when I want matching upper and lower bounds, maybe I can prove a lower bound for G and an upper bound for F, and that will be okay if G is, let me call it, a strengthening of F. And let me warn you that I'm not sure this is 100% standard terminology, but it's kind of clear, hopefully, what would it mean that G is a strengthening of F? Well, it would mean that for any clause C in F, there exists a clause D in G such that D is a subclause of C. Somehow G, then it's clear that G is like a strictly stronger formula than F. And then it stands to reason that we should again have size of refuting G is, well, big O, or actually, yeah, of size of refuting F. For resolution, you don't need any big O. For polynomial calculus, let's play it safe. And again, for width or degree, you get just a less than equal with degree. Okay. So this is hopefully believable. I'll just leave it as an exercise. So what we plan to do today, what we want to do, is to show that we'll start by arguing that 3 is essentially optimal. It's actually, I mean, it's not clear. Maybe I'm not saying like you could think about, are there expressions of some completely different form that you could maybe write in other interesting ways? That's another question. But I'm just saying, like one natural question you could ask is, do I really need width squared here, for instance? Could this potentially hold if I just say width to the 1.5 instead? And we'll say that no, the answer is no. So you really need, because what this expression says is that up to roughly square root n width, we don't get anything out of this. And this is in fact correct, because there are formulas that require substantially wide proofs, but still have very short proofs. This is what we'll see. And then we'll see that the second thing we'll do is that the counting argument is type. And the most interesting thing here is maybe that the technique to prove this that we will talk about, because we need to hack it a little bit. Okay, so what I want to claim now is the following theorem. So let me write it this way. There are KCNF formulas. You could pick K to be 5 or something like this. I don't care so much. You could actually pick K to be 3, but we're going to do it for 5. Let me give the, okay, let's just say over m squared variables. And m cubed clauses, except that I should maybe add big O's. So there are KCNF formulas, let me call them FM maybe, such that the length of refuting them in resolution is m cubed. So basically you just list the formula. This is the best you could hope for, right? If the formula is somewhat non-trivial. But the width of refuting FM is linear in M. And now note that this is square root number of variables. And now just because this gives us a nice thing for free that I claimed before but didn't prove, so let us write it down. I claim this immediately shows that general resolution is exponentially stronger than tree-like resolution. Why? Well, because we have the Ben-Sasson and Wigderson bound that says that for tree-like resolution, any non-trivial with lower bound, we pick it up in the exponent immediately. So for these formulas, which we'll see shortly, they have a size lower bound, resolution size lower bound, or length lower bound. Again, length or size for me are synonyms when it comes to resolution. 2 to the square root number of variables. But in terms of variables, general resolution refutes them in big O of number of variables to the 1.5, 3 over 2. This is not the strongest separation we have for general and tree-like resolution, but it's nice we sort of get it for free from us. So let's just write it down. So we actually did half of this lower bound already. So these are the ordering principle formulas that you might remember from a few lectures back. So let me write them down, what these formulas are. And let me give them names. We're going to have formulas A over I, J, and K, or clauses, and they basically say that transitivity holds. So you should now think of X, I, J. You should think of this as we have a set of elements, and the Xij is true if element I is less than element J with respect to some order. And this, I mean, it should be an order. So if I is less than J and J is less than K, then I should be less than K. This is transitivity. If it's an order, it should be anti-symmetric. So it's not the case that I is less than J and J is less than I. Okay, so now we have a partial order. And then we say, well, except that this is a finite set, but there is no minimal element, or at least element J is not the smallest one. So we loop over all I in N, I not equal to J, and we say that some Xij is true. So this is non-minimality. And then if we want to, we could also require the order to be total, which says that any pair of elements EI and EJ are ordered. Either I is less than J or J is less than I. Okay, so now we only have one problem. So I'm going to use these formulas to show this theorem. Except this doesn't make any sense because these particular clauses are wide. So how do we deal with this? There are two ways to deal with this. One way is to take this formula as is and just convert this to 3CNF using this translation. And in fact, in the lecture notes, we will have a self-contained proof of a lower bound for the 3CNF version of these ordering principle formulas. What we did a few lectures back is instead we changed this formula and said, well, there is some I that is less than J, but I should be a neighbor of J with respect to some bounded degree graph that is an expander. And then we actually, for this formula with A, B, C, and D, except I replaced C by witnesses coming from neighbors in a bounded degree expander, we prove the polynomial calculus linear degree lower bound. Linear in n, meaning square root n in the number of variables. And now the point is that what is this? You realize that if you do it over graph, it's just a strengthening of the ordering principle formula. Okay, so we actually have, this gives us, so So this gives us a degree lower bound for a 5CNF formula. Or you could take the original Bonet and Galesi. I should have said that this is by Bonet and Galesi. And I think so. This is, we're going to take the graph formula, and then the lower bound is already done. Okay. For the upper bound, we are actually only going to use transitivity, anti-symmetry, and non-minimality. So we won't even need the total ordering. And now I claim it's clear that if I can prove a polynomial upper bound on this formula, then that polynomial upper bound clearly holds for the strengthening. And I have a degree lower bound for the strengthening, and then we're home. Okay, does this make sense? Okay, and let's see. So let me give a name to this formula. Let me call it the partial ordering principle over n elements. It's worth noting that these formulas were studied in the 80s. So there's a paper by Krishnamurti in 85, the same year when Haken proved the exponential lower bound. And sort of, you know, for which type of, how do you get a resolution lower bound? Well, here's how you do it, kind of. You take some principle that is true in an infinite domain. For instance, the pigeonhole principle is like satisfiable. Is this Hotel California or something? No, this is Hilbert's Hotel, right? So you know, it is true that every pigeon can fly to its own hole somehow. If you start with pigeons from, I guess, 0 to infinity and holes from n to infinity, then pigeon I or guest I checks into room I plus 1. And there's no problem because you can do this in an infinite model. But in a finite model, it doesn't work. And there are, if you're into bounded arithmetic, which I'm sadly is not so much, but this is actually where the original pigeonhole principle lower bounds for stronger proof systems such as bounded Frege came from like a model theoretic argument. And you take something that is true in an infinite model, but then you fix a finite model, and then it's false, but it's hard to prove. And note that this is exactly the same type of, you know, if you have an order set without minimal elements, that's perfectly fine in an infinite domain. The only problem is the finiteness. So it stands to reason then that this is exponentially hard for resolution. The only problem is like, how can we prove it? And so Krishnamurti conjectured in 85 that, okay, we did pigeonhole, sort of let's do this. I mean, I'm sort of inventing history now. I actually don't know if he discussed the pigeonhole principle. I should have checked this. And there things stood for about 10 years. And then, interestingly, Stålmarck, who is the man behind Stålmarck's method, which is one quite successful algorithm for actually solving SAT in practice, that in particular is used in railway applications for formal verification, I think, still. So Stålmarck in 96 proved that in fact resolution refutes the partial ordering principle in, okay, now I'm switching to n anyway, sorry for this, in n cubed. This n is the same as the m over here. I promised that n would be the number of variables. I realize now I'm breaking this promise. So maybe for a few minutes, let n be this parameter, because then otherwise I'll fry my brain. Okay, so I just wanted, and this is kind of a neat, this is actually somewhat surprising that resolution can do this. And it really, I find this proof very neat. So let me tell you, I'm not going to waste too much time on it, but what resolution does is actually, resolution does an inductive proof. So basically, the proof is by induction. And the base case is for constant k, you can basically just, do whatever. for your favorite k, but you could even pick k to be 2 or 3. I mean, this is a fixed size formula. Just use brute force. I don't care. And the inductive step says build a derivation pi n that takes pop n and derives from it pop n minus 1. And does this in quadratic length. So now you realize if I can do this, then I start with pop n, I derive pop n minus 1 from it, and then n minus 2, and then n minus 3. And finally, when I feel like the formula is small enough, I brute force. And the intuition is, basically that En is not the minimal element. Right? We know this. CNN says that n is not the minimal element. So then you realize that if pop is n is true, then pop n minus 1 is also true. That is, all of the other elements, they are not minimal. This I already know. I mean, this is the formula says. But in addition, the fact that they're not minimal is not witnessed by element n, because that is not the smallest element. So there has to be some other witness. Like whenever En is used to witness something, I can replace it by whatever witness En uses. Okay, and now the only thing is we need to do this. And maybe I'll do it over here. So that we can see what these, I'm going to use the names for these clauses. So here's the idea. Let me see what we want to prove. I want to prove the claim that for any j less equal n minus 1, I can derive Cn minus 1 j. What does it say? It says that j is not the minimal element, and this is witnessed by some of the n minus 1 other elements, but not the element n. Okay. In polynomial length, from what do I need? I will need Cn1 up to Cn n, and then I'm going to use A1nj, so transitivity A n minus 1 and j and b j n. Okay, this is, if I can prove this, then we're home, because then I start with my formula pop n, and then I derive all of these clauses, and note that all of the other clauses in pop n minus 1, they're already there. Yes? Okay. And note that it does make sense that I would use these. So why am I using these particular clauses? Well, I'm using the fact clearly I need to prove that none of these elements are minimal. And the reason I would be interested in using transitivity is that, well, you know, I might be worried that n is in fact, En is the witness that j is not minimal. But then I'm going to work on the transitivity axioms and say that, well, there has to be some other witness that n is not minimal. It's maybe 1 or I don't know, or n minus 1. So I'll sort of just substitute that witness instead. Okay, and now all we need to do is so if we can prove this, then we're done. So let's see, what do we do? So fix, now we're interested in deriving this guy. For every I that are not j, I'm just going to resolve C and J with transitivity, saying that if I is less than n and n is less than j, then I is less than j. And this will give me Cn minus 1j, almost what I want, except I pick up not xi n. Should you pick up two things? No, because, yeah, note that one of these, I'm going to pick up one of these and the other one are already in the end. So this is what you have to look at. Let's see if we can. So should we write this down? So this is x of in or not nj or xij. Xij is already in there. Xin is this one. And this was the guy that I wanted to get rid of. That n was not the witness. So this is what I resolve away. Right? This goes away. This one is already in this clause. And this one is what I'm picking up. Okay. If I is equal to j, then I'm gonna derive, I take C and J and then BJM, so anti-symmetry. And then hopefully we can convince ourselves that we're again gonna get Cn minus 1j or xjn not, because we're going to, again, we resolve away not x and j, and we keep not xjn. Are you happy with this? Okay, but that means that now we have all, so now we just do, we start with C and N, and now basically we're just gonna do Cn minus 1 n or not x 1n, and then we resolve. And basically now, I don't know how much energy we have. You're just going to take Cn minus 1n or not x2n, or, and here you plug in not x3 n. All the way down to Cn minus 1. And the last one is going to be not x n minus 1. Comma n. And now if you just resolve all of these guys, then basically you're going to peel away all of the variables. So what happens? Okay, so maybe let me write down what happens here the first time is now you pick up. Let me write down the first step. You pick up Cn minus 1 j, and then you have an or L goes from 2 to n minus 1 x L n. This is just by looking at these clauses, this is what I want, but now I have a bunch of positive literals. I'm just going to resolve all of them away. So the intuition is really inductive argument, and then you see that resolution can do. If we're happy with this, then we have proven that there's a, if you look at it carefully, this is actually going to be, I guess, I mean, you're going to do, this is a linear length thing. You're going to do it for a linear number of clauses, so it's going to be quadratic. And you do this for all of, and after this, you have all of these clauses, and that means that you have top n minus 1, and we're done. Questions on this, or are we happy? So again, note that, so we had the upper bound for resolution, and we had a degree lower bound for polynomial calculus. And now maybe you can ask, yeah, but wait, do you mean polynomial calculus or polynomial calculus resolution? With some care, because, and the reason for asking is, polynomial calculus without dual variables, can it actually simulate this proof? And the answer is, well, it depends on how you choose your signs, but if you choose them the right way, then you're not going to have a problem. So, yeah. So that's half of the lecture. So now we're turning to the second half, which will take us slightly longer. So it's a bit more than half. We're now looking at the fact that if the width in resolution is W, then this implies that the length of refuting F, in fact, you can say something stronger, right? Without loss of generality, the length of whatever refutation achieves this width bound need not be larger than n to the W. It's natural to ask how tight this argument is. So you could say that it's not clear at all, a priori, what should hold. Like, we don't have tons of formulas in the proof complexity literature, but we do have some. And it tends to be the case that either the formulas have linear with lower bounds, and then they're exponentially hard. But in fact, for empirically, like as soon as, if you look in the literature and you say, oh, I see that my formula has a width lower bound that is less than n squared asymptotically, or even maybe actually big O of n squared, then that has tended to mean that actually the length of refuting F is just a polynomial that is independent on W. Like empirically, if you look at the different formulas we have, this is true. So we didn't have any examples of formulas with this behavior. Clegg and Edmonds Impagliazzo proved that, well, if the width is this much, then there's a polynomial calculus refutation in size at most n to the W. And then they asked, is this tight or can we do something better? And Beam and Pitassi in their beautiful survey, past, present, and future of proof complexity, asked the same thing. A third reason to care about this is something that we will not talk about in this course, probably, although maybe we should, is that there's an interesting paper by Atserias, Fichte, and Thurley, where they try to understand modern conflict-driven closed-running SAT solvers. And they show there are some asterisks, but basically what they show is for a faithful model of what a modern SAT solver actually is, if I run a SAT solver on a formula that has a resolution refutation of width W, just under this promise, and then I do one tweak on the SAT solver, I remove its decision heuristic, that it is when it's not propagating, when it needs to pick a variable, it usually does something clever. Let's remove that and just let it pick a variable at random and set it at random. Okay. Then, under the promise that the resolution refutation width is W, with asymptotically, almost surely, the SAT solver will actually run in time n to the big O W. Okay, and you might say, well, that's not so hard because, just exhaustively generating resolution proofs in width W would give me that running time. But that is absolutely not what a SAT solver is doing. So just somehow, by the promise that the width is at most this, makes a SAT solver that does something completely different run in time n to the big O W. And again, you can ask, is this tight? And obviously, it is tight. It would be tight if it would turn out that there are these kind of formulas that require proofs of size n to the omega of W, because then the SAT solver would need to split out this proof. Okay, so I'm trying to convince you, I guess, that this is the question whether this is tight is somewhat interesting. We should care about the answer. And at least if there's a nice guy giving a lecture who's going to explain to you what the right answer is. Because it turns out that this is tight, and this is what I'm going to tell you now. And in fact, you can ask similar questions again. We know this for polynomial calculus. There's an analogous result. This is also tight. I'm not going to prove it, but I'm going to tell you essentially all the ingredients so that you can immediately prove it yourself. And then you can go higher. You can go to Sgall-Adams, and by what we're doing today, you can, with a little bit of extra work, you get it for Sgall-Adams also. And then we talked very briefly about sums of squares. It turns out that what we do today cannot give you that result for sums of squares, but it is known how to get it in another way.
So what about the constants in the exponent?
They're not too bad. You mean like, are they galactic or inversely galactic? They're not too bad. Let's see if I'm going to... Oh, I'm not going to state them for you. It's something like, for resolution, it depends a little bit. Did I write this down? It's something for resolution. We're actually going to get this. Okay, we're going to obsess firstly about, I'm going to do this for 3 CNF formulas, which is the smallest width that I could possibly. Note that I want the width of the formula should be constant. The width should not scale with W. That's a little bit cheating. I want this to hold for 3 CNF formulas. And I'm going to get, I think, something like, say, when the width is W, I think my lower bound will be maybe n to the W over 4 or something like this.
And the upper bound is something like n to the 2W, or what's the counting argument?
But no, it's better than that. It's going to be something like, that I'm going to state exactly. So it's going to be something like, it's going to be W to the W times n to the W, I think. But even for tree-like resolution. So there's going to be a tree-like resolution proof of, and if W is a constant, then you're going to get the upper bound, but you're going to have a tree-like upper bound like n to the W, something like this, and a general resolution lower bound, something like n to the W over 4. And then if you allow me to instead prove the results for 4 CNF formulas, then I can immediately gain a 2 in the exponent. But of course, we would not settle for anything less than 3 CNFs in this classroom. I hope you agree with me on this. You get worse bounds. For polynomial calculus, you lose a factor 2, but that's basically because we lose a degree. We're gonna, at the end of the day, this is all gonna end with the pigeonhole principle. We can't avoid it. We're doing proof complexity. So the pigeonhole principle has a tendency to show up, and the quality of this lower bound is going to depend on what we can prove for the pigeonhole principle, and there we lose a factor 2 for polynomial calculus compared to resolution. So we lose that factor 2 in the exponent. For Sgall-Adams, I don't remember if we lose something more. For SOS, you have to do something completely different, and the constants are pretty terrible. I won't talk about this at all. This is a paper by Lauria and Nordström from 2017, maybe. But it's going to require something completely different. Okay, So what I want to prove now is, let me state the theorem and let me maybe philosophize a little bit and then we'll have a break. We're running a little bit over time, but we also started super late today. So I'm blaming the late starting time. So what I'm going to prove to you is by Atseas, Lauria, and myself. And the result is something like the following. Suppose that W is a parameter W of n, which can be super constant even, but not ridiculously large. It's at most, it's strictly smaller than square root n. Then there exists three CNN formulas. F, N, W that have N, W clauses, N variables, big O of N variables, and have the following property. One, the formulas F and W have a resolution refutation. I such that the length is n to the big O of W. The width is big O of W, because that's a width upper bound. And we're not going to talk about it, but since we're starting to talk about space next week, let me just say that this is basically saying they're simultaneously easy with respect to length, width, and space. This is what I'm saying. This is an easy formula. However, not too easy. Any refutation in resolution, in polynomial calculus, let me even throw in dual variables and be multilinear if you like, or Shirali-Adams, any such refutation has size n to the big omega of W for a not terrible constant. And okay, is the statement of the theorem clear? So the one interesting aspect of this is that it's kind of clear that you won't get this by standard tools. So how could you try to get this? Well, you could say, I know Ben-Sasson and Wigderson. But now there are two problems. So we know that Ben-Sasson and Wigderson gives us nothing for width less than square root n, which is one parameter regime that we're interested in. Which is the parameter regime that we are interested in. And we know from what we just did that this is tight. So there's no hope of finding anything else. And even if we somehow, even for large W, we get a lower bound. The lower bound is something like 2 to the W squared over n, which is at best 2 to the W, right? Always. So, and we are shooting for n to the W, not 2 to the W. So like we have the wrong base. Another thing that we have not talked about so much because we didn't use this language, but we'll do it today. What about random restrictions? So the idea with random restrictions is you start with a set of formulas. Fn. And now you design some kind of family of restrictions over a distribution space, say mathematically, calligraphically, fancy style calligraphic D sub n. We sample rho n from this, and we make sure that they are somehow coupled so that, say, Fn, when you restrict it by rho n, this gives me a smaller version of F, or some smaller version in the family. How would you do this? Well, for a pigeonhole principle, we saw this already. You sort of pick a few pigeons and you send them to holes and then you simplify. So this equality sign should be understood as, well, after relabeling things and like cleaning up and okay? And now, what could you do in rho? Well, if rho sets a random literal to true, then this removes, by an argument you've seen, actually, this removes like a fraction W over 2n of wide clauses. If I can pick rho to be suitably random. Now, suppose that the size of proof, that the proof has size S. And suppose I do a random restriction in R rounds. Then let's do the math. Like how many wide clauses do I expect? Well, I expect something like 1 minus W over 2n raised to the power of R times S wide clauses. And now, if I pick R to be something like, just by doing the math, 2n over the width W times log S, then this sort of tells me that the expectation is essentially 0. But then separately, I argue that, well, actually Fm requires large width. So like if M is somewhat non-trivial, then I actually have a lower bound that is, a lower bound that I expect some wide clauses to have survived. So this must be a contradiction unless S is very large. Unless S is so large so that this can only happen after n rounds, essentially. But again, so you do the math and it turns out that you get, if this works, this gives you something that, again, that S is something like 2 to the W. And obviously I cannot pick, if I would pick R larger than the number of variables and restrict all of it, I mean, then definitely the formula is gone. So Ben-Sasson and Wigderson and random restrictions, the way we usually do them in proof complexity. So by the way, I mean, the lower bounds we did for the pigeonhole principle and for shaping could have been phrased also like in this random restriction framework. I didn't do it, but it's not so hard to. Like basically, I mean, we did this prover defendant thingy. Basically, the random assignment that the defendant chose to know how to play was the random restriction. We just expressed it in a different language. So what this tells me is that the standard toolbox will not give n to the W lower bound. But so we need to tweak it a little bit. And this is what we're going to do. So let me tell you what the tweak is. And then we'll have a break. And I'll try to prepare the board. And then we'll try to do this lower bound. At least we won't do all of it. I'll leave some of it as nice exercises for you. But I'll try to do like, there's a key lemma that is like the fun part. And we'll try to at least do that.
Is it 2 to the n or 2 to the W?
That is a W. W as in the width. Okay, so our refined method are going to use random restrictions. So again, we start with some formula family. And then we have some cleverly chosen random restrictions. And they should treat Fn in some nice way. Except we're going to get now some F prime of M instead. So a different family. What is F prime going to be? Spoiler alert, we're going to get pigeonhole principal formulas, but actually of constant size. Pigeonhole principal formulas with W pigeons and W minus 1 hole. And now the argument we had before is like basically the standard random restriction argument says now, if C, the standard restriction argument says, well, if C is wide, then almost surely it is satisfied. And then we do our random restriction and we get what we want. Okay? But now we're going to say, well, maybe I don't know if this happens, but I'm going to say, suppose that C is super wide. Then this definitely happens. Okay? But now I still have the problem, you know, what do I do if C is just somewhat wide? It's too wide, meaning it has to go because I'm going to, in order to get a contradiction, I need to get rid of all wide clauses, also the somewhat wide ones. And the problem is that maybe, I don't know, but it could be that rho does not manage to satisfy C, and that's very, very sad. But I'm going to argue that it's not for lack of trying. Okay? So in fact, rho is like, our random restriction are going to be rho is hitting C over and over and over again, unfortunately missing, right? It's failing to satisfy C, but it's hitting it repeatedly. So what happens when you hit and fail to satisfy literals? Well, at least they go away, yes? So C restricted by rho will have shrunk significantly. How much? Maybe not by too much, but at least somewhat. So that we now move from somewhat wide to actually not wide at all. And now we can run the standard argument. So this is like the new thing. In a standard restriction argument, you just say you sample the restriction, and then if it satisfies your clause, you're happy, and otherwise you give up, and that's very, very sad. And here we have a more refined analysis that we say that, well, either you satisfy, or we argue that if you don't satisfy, then at least you're very likely to shrink the formula substantially. And that turns out that this will allow us to get lower bounds on this form. So now let's take a break, but before we do, are there any questions on this? Because now basically what do we have left? I need to tell you what the formula is. I need to tell you what the random restriction is. And then we're going to need 3 lemmas with one upper bound and 2 lower bounds. And I think we're going to do one of these lemmas, and the other 2 I'm going to leave as exercises.
Is there a guarantee that it doesn't shrink too much? Like it's going to be unsatisfied, right?
Oh, yes. But in this, yes, how, and I'm going to guarantee this in the same way as for the pigeonhole principle. I mean, if I just, for pigeonhole principle, if I just pick a constant fraction of pigeons and send them to whole, and I do this via partial matching, then I'm not worried about killing the formula. It's a good question, but yeah, rho will have to be aware of the structure of F. Yeah, so that's a good point. You will see when we have the construction, this is not a problem at all. Any other question? Then let's take a break. Okay, so we're back after the break and we've filled the board with beautiful symbols. Recall, what do we want to prove? We want to prove that there is a formula that is refutable in width W, and hence also size n to the W, except for constants. It also happens to be easy with respect to space, but we won't talk about that because we haven't really talked about space yet. So we'll just focus on shoots. We'll focus on the markers not getting away. We'll focus on these upper bounds for resolution. And then we say that, oh, but actually this size bound is tight, and we will prove this for, definitely prove it for resolution, and we'll kind of, you'll see in the proof that actually this should not be hard to get for PCR. That's the plan. So we just need to find a formula. And our formula is going to be so-called relativized pigeonhole principle formulas. So relativized pigeonhole principle formulas say the following, that I have a large set of n pigeons, and I have only k minus 1 holes. And now the formula, the relativized pigeonhole principle formula says there is some way of choosing k pigeons out of these n pigeons so that these k pigeons can fly in a one-to-one fashion into k minus 1 holes. How do we formalize this? We formalize this by saying there are two partial functions. A partial function p from 1 up to k to 1 up to n. This is actually a total function and it is injective. It is one-to-one. There is also another partial function q that maps n to k minus 1. It's partial, but it's defined on the range of p. And it is also one-to-one. It is injective on the range of p. So this tells me that the composition of p and q gives me a one-to-one, an injective mapping from k to k minus 1. How do I write this down? Well, let me tell you the obvious way, and then we're going to need to tweak it a little bit. But we're going to encode p and q in the obvious way, just indicators. P, u, v just is true if p of u is v, where u lives in 1 up to k and v lives in 1 up to n. Q, v, w is true if q maps v to w. And then I have rv variables that keeps track of whether v is in the range of p. These are just Boolean variables. And now I have the following functions, following clauses. These clauses for all u's in k say that every u gets mapped somewhere, and it's not the case that two different u's, u and u prime, get mapped to the same v. So this is sort of, I omitted the functionality axioms. I don't think they're really important. This is essentially saying that p is a one-to-one mapping. And then I'm saying that if, whoops, it's wrong. If p u v is true for some u, then v is in the range. So if any p u v is true, this forces rv to true. So this now defines an injective function p for which I have encoded the range. And now I say, well, if v is not in the range of p, then all bets are off. Then you don't need to do anything. This will be very important for us. Like, these variables are absolutely crucial. But suppose that v is in the range, well, then q has to map somewhere. Q has to map v somewhere. And also, if v and v prime are both in the range, then v cannot map both of these elements to the same w.
Do we need the first two R variables for R5? Can't you just have that q bar dw or q bar d prime w?
That's a no. I think I really, we can talk about it. I think I want all of my R variables, and you'll see why in a bit. Okay, So actually, I could do the proof for this, but except that now the problem is, so note that I have changed now so that U, V, and W range over these domains. And the W in my theorem statement is now K. So pedagogically speaking, I'm not sure that this was a great move, but I realize now that this is how it happened. So now the point is that K is, we want to prove n to the K lower bounds for this formula. That's what we want to do. But the problem is, I'm cheating you because clearly the width scales with K, and that's not good. So we have to make it into 3CNF, but we'll do it in the obvious way. We'll just take these clauses and add y variables to turn them into 3CNF. So we have PU1 or PU2 or YU2, and then for all other v's, we have not UV or PUV plus 1, or that's not a not, YUV plus 1. And then the final clause is not YUN minus 2 or PUN minus 1 or PUN. Okay, so this is basically this is the 3CNF version of clause R1. I do exactly the same thing for R4, except I also have to pick up B here. And then, strictly speaking, this is a for clause. So what I'll do, I'll just encode if RV is true and RV prime is also true, then I just have a pair of variables that says RV V prime. This pair of variables blows up. This is where I think I lose a factor of 2 in the exponent, if I remember correctly. And then I say, well, RV V prime just says if both of them are in the domain, then injectivity holds. So now we have a 3CNF and we can work on this. Does this make sense? And if you just check now, apparently I think we have like kn squared clauses and n squared variables. And just to note that if I had left R5b, then I could have gotten a slightly better bump. Which is maybe, this is the kind of thing that I'm debating with myself whether I should ask you to do on the problem set. Let's see. So what is our plan? We will define a random restriction distribution. Oh, I want to give a name to this formula family so we can talk about it. These formulas are relativized pigeonhole principal formulas with k pigeons picked out of n and sent to k minus 1 holes. Obviously, these could be any parameters, but I'm fixing them to k and k minus 1 and n. I just need that this guy should be smaller than this, and this should be like substantially larger for things to be fun. And then this formula is then also the relativized pigeonhole principal formula with k pigeons chosen out of n and sent to k minus 1 holes, except it's a 3CNF version. This is a y tilde. Okay, so what are we going to do? We're going to define a random restriction. And we're going to argue that you take the relativized pigeonhole principle and you hit it with rho, and this will be just the standard pigeonhole principle formula. So this is the first step. And then we're going to do a width lower bound for the pigeonhole principle formula. And by now, we're pretty good at this, so this is going to be fast. And then here comes the miracle. We're going to say that suppose we take the refutation of the relativized pigeonhole principle formula. And we're going to say if this refutation is small, then, well, we know that restrictions preserve refutations. So clearly, if rho sends the relativized pigeonhole principle to the pigeonhole principle, then pi restricted by rho refutes the standard pigeonhole principle, and it has no white clauses. That's very surprising, because we just proved that that is not possible. So in fact, let's be more precise. So if I would have n to the little o of w here, this happens. So hence, the size of such a pi is n to the big omega of w. And then finally, I need to show that the width of refuting RPHP is it's going to be big O of k. And then if I want to be a little bit careful, I also claim that in fact this is a tree-like. We can make this derivation. I mean, already from this with the lower bound, I'm kind of home. I get n to the k, but you can actually make the refutation tree-like. But I'm not sure we're going to do that. So this is what we need to do. And we still have some time.
Reset.
Yeah, no, we have scheduled from 1 to 4. No? I was somehow thinking that it was 4 p.m., but it isn't. So that's great. So okay. So what should the random restriction do? I have this relativized pigeonhole principle, and I want to get the pigeonhole principle.
Get rid of R.
Say again?
So get rid of the R variable.
I should get rid of, yeah. So the random restriction should, yeah. How do I do this? Well, I just somehow, basically what I will do is let me select P and plug it in. What will happen if I do that? Well, then on the range of P, I should sort of get, it stands to reason if you look at this, like if all of these disappear, then you see that I sort of have a pigeonhole principle here, no? Okay. But there's a lot of Q that doesn't talk about these. I mean, n goes to infinity and k is constant. So there are going to be tons of clauses here that actually are not the pigeonhole principle. What am I going to do for those? Well, for those, I'm going to make sure to set RV false. And then I'm going to go crazy on all of these variables and just flip coins. So provided that I make sure to get a lot of R's false, so this I don't want to do random at all. I'm definitely, as soon as I can, I'm going to set my RVs to false, but then I have tons of variables that I can flip at will. So most of, like the overwhelming majority of the variables in my formula are going to be restricted. It's a massive restriction. Am I making sense? So that's the idea. So let's see if we can do it. And if we're actually, I'm planning on removing the theorem statement now because, well, because we have, it's always, it's easier to have plausible deniability if you don't remember what we were proving. And plus, I wanted, I think, to define the random restriction. Let's see if I can do it. In this space, or if I need more space. So what my random restriction, it's going to be a distribution D. It's formed in the following way. So I'm going to pick a set S in N of size K uniformly at random. This is how I start. This is basically, I'm choosing where P should send, which pigeons P should select. And then I just fix arbitrarily, I really don't care. I send the pigeons to the selected set S. Okay. So now I need to define row. So for V, RV, it's going to be true if V is in S. I'm going to say that V is a selected or picked pigeon in this case. But note that very few pigeons are picked, K of them are. Otherwise, I set RV to false. Obviously, R row on RVV prime is row of RV and row of RV prime, right? So these are these guys here. I just set them to make sure that this is intending meaning on RVV prime. So this is just an auxiliary variable. Row of PUV is then it's also fairly straightforward. I mean, it's true if psi of u is V, where psi is this fixed thing, this fixed mapping, and otherwise it's false. So note in particular that I'm just going to satisfy and remove all of R1 and R2. Assuming, okay, except I didn't, let me say that, and maybe what are these variables called? Y, UV are just set so as to satisfy R1 prime. It's clear we can do this because every white clause is going to have one variable set to true. So basically, all the y's before that I set to true, and then I flip the false afterwards, something like this. Okay. So now comes the more interesting part. What do I do with the q variables? And what do I do with the z variables? These are these guys, QV and ZV. Let me actually say before I forget that all of these variables, they mention they mention pigeon V. Okay? And what I'm going to do now is, well, if V is one of the selected pigeons, then I should leave this unassigned. Otherwise, I'm going to flip a random BV with a perfectly unbiased coin and set QVW to this random bit. But it's just, it's a bit that is flipped for the pigeon V. And same thing for Z, if V is a selected pigeon, then I shouldn't touch it, and otherwise I do the same BV. This is my random restriction. And now what did I do? If you think about it, if you look at this formula, because it's maybe easier to see, we kind of got rid of all of this. We satisfied it. We satisfied all of these. And now these clauses kind of forced, actually, and RV made sure that we satisfied all of these. So they're now gone. And here, when RV is false, they just vanished. So maybe take another color. So these are gone, always. And the clauses survive for V and V prime that are selected. Do you agree with me? This is just, we're not doing anything strange. It's just like a 2-minute offline thing.
Real quick question. Why do we randomly set the Qs? Why don't we just set them to like 0 or something?
We'll get it. Okay. Get it. It's super important. Why do we want, because basically, why do we set them randomly? Well, because so what do we want to do? We're going to get a refutation with lots of wide clauses. We want to argue that this restriction satisfies the wide clauses. We have no idea what a wide clause is. It's an adversarial, very non-random object. Okay. So in particular, if I tell you how I'm going to set that, and what do I do? The row should satisfy this clause. But if I tell you for every single variable how I'm going to set it, then of course you'll build your clause so that it isn't satisfied. So that's why for as many variables as possible in your clause, I want to flip a random coin. Because then you realize that suppose that your clause has width W and I get to flip W random coins, then your clause is going to survive with probability 1/2 to the W, which is going to be extremely small. But this will only happen if I have lots of independent variables. Is this making sense? Good question. Okay, so I claim that if you look at our PHP, picking k pigeons out of n and sending them to k-1 holes, and you hit them with this restriction that is sampled from D, and you relabel, let's say that, let's just rename the set S so that it actually selected pigeons 1 up to k. Clearly, I can just rename. I mean, it doesn't really matter. Then this formula will now be the following clauses. I'll get QV1 or ZV1, and then I'll get not ZVW or QVW W plus 1 or ZVW plus 1 for W ranging all the way up to k-3. And then I have not Z V k-3. And then the final two Q variables, QV k-2 or QV k-1. And then I will have not QVW or not QV prime W, where V prime will range over 1 up to k, but being distinct, and W always ranges up to k-1. So I claim that this is just that, like, here's the original formula, here's the random restriction, take a cup of tea or coffee, sit down and just write things out carefully, do the renaming of the S set, you get this. But it's also hopefully believable from like the intuition behind us. Okay, so now, in particular, we have note that these are all the variables that remain. Okay, so all my clauses now are over variables like this. So for any clause, also for original clauses in the original formula, let me define the pigeon width of any clause, also for these clauses definitely, but also for the original R PHP clauses. The pigeon width of a clause D is just the number of mentioned pigeons. Okay, and it stands to reason also, like if you want to do the polynomial calculus, we're going to define the pigeon degree of monomials, and you can kind of guess what that definition is. So now I'm just going to claim some things. So lemma 1 is the following claim that any resolution refutation pi of Okay, I want to give a name to this also. This is what we call the pigeonhole principal formula for k pigeons in k-1 holes. It's a slight, I mean, this is a slightly funky first clause, but except for that, I hope you're happy with this. Okay, so I'll refer to this formula as tilde PHP. So any resolution refutation of this formula has pigeon width at least k-1. So essentially, you know, you're not going to refute this formula unless in some clause you mention all pigeons except one. Okay, and this is where here is one difference for PC. You're going to get here k-1 over 2 rounded upwards, for instance. Okay. How do you get this lower bound for resolution? Exercise for you guys. How would you do it? Well, you basically, we know how to prove, we know that lower bounds actually follow from defendant strategies. And now width is kind of, if you think about it, is how many assignments I remember. Except that now I think of pigeon width, so now I'm going to count for the prosecutor how many pigeons is the prosecutor aware of. And now, clearly, I argue that, well, if I take a resolution refutation in small pigeon width, then that's going to give me a prosecutor strategy that doesn't ask about many pigeons. Okay? So in particular, if I can give a good defendant strategy against prosecutors that don't remember enough pigeons, then that shows that in addition to all other things, there's definitely no resolution proof. Okay, so now I leave it to you. As a defendant, you know that the prosecutor is never mentioning more than k-2 pigeons or something. Actually, k-1 because there's going to be a small loss. You're going to be able to, you need to be able to play successfully as long as prosecutor doesn't remember all pigeons. Think about how to do this. Exercise. For polynomial calculus, this is a little bit more complicated, but basically you go back to the way we did it, is we use Razborov's original paper from 1998, the one with the R operators. And then you have a little bit of a problem because that paper doesn't work with this encoding, so then you have to sort of do a translation, and then you work it out. What do you do if you don't have the energy? I mean, didn't we do a pigeonhole lower bound? We did. So you could plug in Nordström in here, but then you're not going to get this beautiful bound. Then you're going to get some terrible constant. But you're still going to get a big omega. But like, I mean, this is essentially tight. If you want the tight results, you go back to Razborov. If you're happy with this qualitative and you don't worry about the constants, then just plug in Nordström and you're good to go. In fact, if you plug in Nordström, then what we will do now will be sufficient to give you something for polynomial. Okay, so the key thing that we need, the fun part now. So let me state the fun lemma, and let us then carefully just go over it, because I think for some of you, you've seen it before. Some of you, maybe this is the first restriction argument. So let me be a little bit careful. I'll state the magic lemma, and then we'll just convince ourselves that indeed this is what we want. And then we'll do the magic lemma, except that we'll have to debate how much calculations we want to be on the whiteboard. Most of them are in my notes, so maybe we'll, leave them there. I'm not sure. So here is our key lemma. The lemma, okay, what will the lemma say? The lemma will say something along the lines of, take any clause and hit it with the random restriction row. Then after that, that clause is going to have small pigeon width. How could it have small pigeon width? One of two ways. Either it's satisfied, then it has very small pigeon width indeed. It vanished. Okay. Or maybe I didn't manage to satisfy it, but at least I shrunk it significantly. Okay, that's how the proof is going to go. The statement says that we have K, we have L, we have N natural numbers. And then N is not too small, 16 is enough. L is at most K, K is not too large, but it can be fairly large, N over 4 log M. These are bounds around. I mean, there's a lot of robustness in here, but I'm just putting down what we have in the paper. A is any clause over the variables in the relativized pigeonhole principle formula. K pigeons out of N to K minus 1 holes, and let's add the auxiliary variables. And rho is sampled from a random restriction calligraphic D. Then the probability, so with probability, only probability over rho now. So getting back to this question, note that A is any clause. I have no control. It's a worst case object. My only randomness is the distribution. So with probability over the randomness of the distribution, that the pigeon width, the probability that the pigeon width of A is less than L, that probability is at least, it's very likely, it's essentially probability 1, except for 4k log n raised to the power of k over n raised to the power of n. So A is not a pigeon-wide clause except with polynomially vanishing small probability. And note that, okay, yeah, so this is the claim. And let's see if I can do the proof. So here is pi. So now I claim that we can prove a lower bound on the size. So we have a refutation of the relativized pigeonhole principle formula. The size or the length is S. Hit it with a random restriction. And pi rho is a refutation of the pigeonhole principle formula with k pigeons and k minus 1 holes. Okay, right? Because rho sends RPHP to the pigeonhole principle formula, and random, any kind of restrictions preserve resolution refutation. So what do I know about this? Well, it's a refutation of the pigeonhole principle formula, so it has pigeon width k minus 1 with probability 1. You agree? I mean, this is, yes, we even have the lemma on the board. Okay. Definitely, there are pigeon-wide clauses in here. Okay. But every individual clause is very unlikely to have large width, right? The probability that a single clause, let's write it down again. So the probability that a single clause has large pigeon width is actually less than this. pigeon width. Now I want to plug in pigeon width k minus 1, so I'm fixing L to be k minus 1. For a single clause, this is the probability that the clause has pigeon width k minus 1. This is an upper bound. What is the probability that some clause in the proof has this large pigeon width? Well, I don't know. These are highly dependent events, but we're given an upper bound. So if I want to know the upper bound of the union of S different events happening, is just the sum of the probabilities of the S events happening. Yes? So just by union bounding, the probability of actually having pigeon width greater or equal to k minus 1, that is less than number of clauses I have times this probability. But I know that this is probability 1. So the only way this can be probability 1 is that S has to be somewhat large. How large? Well, apparently n to the k minus 1 over 4k log n raised to the power of k. Does this make sense? Again, what did we do? We took a random restriction and we said that, the proof again has two components. We have argued that the random restriction sends the formula to some other kind of formula. For this other kind of formula, we have an ironclad lower bound. This is the pigeon width. We know that whatever we do after our restriction, we will have a refutation of this guy, which has to have large pigeon width. But we know that then we look at the individual clauses in our refutation, and we see that the probability that any single clause is a witness of this happening is exceedingly small, like super small. And yet we know that this must happen. So then by a union bound, I have to have many chances to find a witness, because every single witness is so likely to fail. So the only way I can get this probability above 1 is if S is the inverse of this, which is the bound we're after. Okay. Good. So now, provided that we're happy with this, we are almost done. Well, we have two things left. We need to prove this lemma. And we have a final punchline lemma. And let me write it down. Namely that these formulas are not hard. This I didn't prove to you yet. So this is lemma 4, which is going to say that I claim that the relativized pigeonhole principle formula, selecting k pigeons out of n and sending them to k minus 1 holes, this formula has a tree-like resolution refutation. Pi, such that the length of pi is big O of k to the k n to the k. And the width of pi is 2k plus 1. Okay. How do we prove this? Know the answer. It's an exercise for you, probably, maybe, on the problem set even. Let me tell you basically what you should do. Well, again, we're going to use the equivalence. By the way, I don't know if you noted this. So like we did our first resolution proof for the pop n principle. Right? How informative was it? How easy was it to understand? Okay, some of you think it's fine, but somehow, I mean, manipulating these clauses, at least for me, like, I really don't want to do my resolution proofs in this way. It's so much nicer to just be the prosecutor and then keep track of your record. And this is what I suggest to do here. So you just, and you need to argue now that I'm going to be a prosecutor and I'm never going to forget. And yet I don't have too many records. What would I do first? Well, first, I will figure out, let me figure out the P mapping. So I will just ask about, for every U, I will ask where P maps it. And note that this is where it's very convenient to have these extension variables, because I'm going to ask whether U maps to hole 1 and hole 2. And if that is not the case, then this Y auxiliary variable says that, well, I haven't mapped it so far. So I asked about this, and either the defendant loses then and there, or I can forget PU1 and PU2. So I just keep walking along these clauses until for 1, U equals 1, I figure out where P sends it. And then I do it for U equals 2, and then for U equals 3. And basically, in memory at most K. Now this is the standard prosecutor-defendant game. No pigeon width, no nothing. Okay? So essentially, in memory K, I figure out what the P mapping is. Okay. Good. Now I figured out the P mapping. Then let me figure out the range. And again, this is sort of easy. In fact, as soon as I know where something maps, I can just convert and say that that's the range. Actually, no, I need to. I first figure out all of P. This I probably need to do because I need to prove inactivity. Once I have all of P, I asked about all the range variables. That's going to be an additional memory K, but we can afford that. We have 2K. Now I can forget. Once I have the range variables, I forget all about my P's. And now I just need to, now I know which part of the Q formula I should work on to force contradiction. Okay? And now the tricky part is to figure out that I don't get more than this many records. And this in particular means, I mean, this then can be simulated by polynomial calculus. PCR is obvious, polynomial calculus not so hard to show. For Shirley-Adams, you need an argument. If you have Shirley-Adams with dual variables, then it's not so hard. If you have Shirley-Adams without dual variables, you have to work a little bit. But basically, it's going to be fine because the degree is bounded. Okay. So all we have left now is the restriction argument, the restriction lemma. And I'm desperately trying to find something that we can erase. Let's see. I'm going to do the proof for clauses. It's exactly the same for monomials. All the things that we're going to use is that clauses and monomials have the property that if I get a hold of a variable that I can set freely and I set it randomly, then with probability 1/2 it makes the monomial go away. Or with probability 1/2 it makes the clause go away. And then depending on how you should set it 1 or 0, that depends on which algebraic mood you're in today. Which is incidentally why to avoid this, I'm sort of carefully using true and false here to avoid any confusion. So for simplicity, let's agree that A is a clause, but it could be a monomial. It would be exactly the same. Let's say that A mentions pigeons V1, V2 up to VR. As witnessed by literals. I mean, I don't know what it means that these pigeons are mentioned. They could be mentioned several times, but at least there's one literal that there's one literal, either a Q or a Z, that mentions this particular pigeon. Let's fix one. So I have A1, A2 up to AR. Okay. Let's suppose let me sort the pigeons in order, just for quick. And now we have a case analysis. The case analysis is large pigeon width. What do I mean by large pigeon width? I will mean that the pigeon width is larger than 2k times log n. And then we're going to have small pigeon width. Which then is r less than equal to k log n. I don't know which category A falls into, but we're going to prove good things in both settings. So in the large pigeon width setting, we're basically going to prove that A restricted by rho is 1. Pretty much, almost sure. So it just vanishes. I don't know that in the small pigeon width setting, but note that as we discussed, rho is pretty aggressive about fixing variables. So if it didn't set A to false, to true, then at least it was hitting A massively, and the intuitive thing is that, well, either A already had small enough width, and then of course we're not worried, but otherwise, sort of, we want to say that A restricted by rho shrinks to small enough width. That's the plan. Does this make sense? Well, then I guess that there is not too much to do, right? We just go ahead and do it. Suppose that R is large. Then the probability that A even survives, well, firstly, it is less, I mean, a necessary but not sufficient condition is that the literal is not set to true. I mean, if as soon as any of these literals are set to true, the clause vanishes. So clearly none of them are set to true. For I equals 1, 2, all the way up to R, actually, let me cap this at the 2k log n. And let me maybe, just to say typing, let capital K be 2k log n. Okay. So I'm just saying, in order for A to survive, rho has to not satisfy the first 2k log n of these guys. And then maybe there are more, but let's just focus on 2k log n. This is going to be I goes from 1 to k. The probability that just by conditional probabilities, the way like this works, this is the probability that rho doesn't send AI to true, conditioning on that things didn't break already. So let me write here. J less than I. This I'm just using as the probability of events A and B both happening is the probability of A happening times the probability of B happening, conditioning on that A happens. This is just what I'm using here. Okay, let's think about what could happen here. How could this happen? There are two cases. It could be that VI is picked. It could be that the coin flip is wrong. Right? These are the two ways how this can happen. Like either VI is actually picked, and then obviously rho will leave this unassigned. Otherwise, if it didn't, maybe we flipped the coin and we were unlucky. Yes? Okay. But note that if I'm flipping a random coin, then I don't care about the conditioning. It's a random coin. Okay. What is the probability that VI is in S? Well, that probability is maximized, obviously, if, as of yet, I have not picked any other pigeons. So I'm going to replace this by conditioning on that Vj is not in S for j less than I. This can only increase this probability. Okay, but then, okay, and that means now that means that we now have a less than equal here. Let's keep working on this. So again, we have these two scenarios. Now and note that these events are mutually exclusive, right? But so if it's a coin flip, then we get the wrong coin value with probability a half. Otherwise, we need to select where we haven't selected any pigeon yet, so we have k pigeons to select. And k chances that we will hit the pigeon we're talking about now. And thanks to the fact that we didn't select any pigeons so far, this is where we're driving this denominator down to increase this probability. Okay, and now we know that I is less than k, which is less than 2 log n. So kind of. I mean, this is almost 1 over n. It's not quite, but it's so if you, I'm actually gonna just be a little bit lazy and say that this is 1/2, this is at most 4 over 8, and this is like at most, you know, push things large enough, this is at most 1 over 8. So we get this, where actually, let me then change, and I don't need the rounding any longer. I'll plug in 2k log n without the rounding. And then you work it out. So now you see that, well, this raised to the power of log n, that means that I'll get n down here raised to some constant, and when the dust settles, you get 1 over n to the k. There's like a lot of slack in this argument. Basically, this is the easy case. If the pigeon width is large, then you know there's no chance on the planet Earth that this closer, right? You don't need to work. You buying this so far? Now, finally, we get to the novelty, the new argument. which is this thing where okay, suppose that R is in fact less equal to K log n. Round it down. The fact that R is small means that we can now not argue that rho is likely to hit and satisfy the clause. But note that we know that we know that rho picks K pigeons and leaves them unassigned, which means that almost all pigeons, like n minus k, essentially all pigeons get picked and get fixed so that these variables disappear. Clearly, if rho messed up and set them all with the wrong sign, then A survives. But it must have shrunk significantly, right? In order to have pigeon width, in order to have pigeon width L, it had a very few pigeons to begin with, and pretty much like a super large fraction of them survived. That's amazing. I mean, that seems very unlikely. Yes? Okay, so now all that remains is the math. So, so the number of choices of S with exactly I pigeons mentioned in A, the clause that we're looking at, is, let's see, so A is mentioning R pigeons, and I should choose I of those. And the remaining K minus I pigeons, I should choose from the other guys. And now the point is, we're just going to say, okay, somehow we have to hit such a successful choice for some I that lies between L and K, which is the maximum. So the probability of L surviving pigeons is, I just sum up for I goes from L all the way up to K, which is the maximal pigeon width. Well, here are the ways fixing I. Here are the number of successful choices I can make. Here is the total number of choices, and choose K. Okay, so now you know which one of these terms is the largest. So firstly, because R is not large and K is not large, I can sort of just max them out. I can say, how many terms do we have here? Well, clearly less than K terms. And which one is the largest one? Well, if I take R to be max, what it could be 2K log n, rounded down, over K. And then just to make sure I'm not losing anything, let me throw in, let me not write n minus K. Let me actually allow here to choose from all n of them. And K minus L divided by n choose K. And you kind of see what is happening here. That there's like an amazing amount of slack in this argument. And now basically, now what remains from here on is just to do calculations. And I'm debating with myself, and I'm not sure if we have the energy to do this. Maybe I'll just right calculations. And when the dust settles, and now what are we going to use here? This is where we use that k is not too large. So we're going to use that n. So n is not too small, and k is not too large. So in particular, one thing that we will use in our calculations, just to write it down, is we definitely know that k is less than n over 16. One other thing that we do know, so then basically we're gonna get things like n to when we compare n and n minus k, that means that we're going to pick up numbers like 16 over 15. And later in the calculations, this gets raised to the power of L. And we will need to argue that this is not too large. And if you just, I don't know if I have a beautiful argument for this, but if you just basically brute force it, you convince yourself that this is true. That basically, for any L that is at most k times this small exponential thingy is definitely not more than 2 to the k. And then you end up with something like, later in the calculations, you have something like, k times 16 over 15 raised to the power of L times 2k log n over n raised to the power of L, and this raised to the power of k. And now you see, okay, this was at most 2 to the k. And so we get something like 4k log n raised to the power of L. And this is raised to the power of k. And honestly, this is like, you just have to sit down with the calculations and work them out. But the intuition, like why should this work? Again, you have fairly few pigeons, and rho is selecting very few pigeons. So you somehow, out of these pigeons, very, very many should be selected by rho. But there are only so many ways you can do this, and this number is going to be so much smaller than this. And then you just do some estimates, but the estimates, you don't need to be very precise. So, modulo the fact that I'm cheating you on the calculations, this proves lemma 3. So where does this leave us? Well, this tells us now that for resolution, since we had a pigeon width lower bound, this gives us an n to the big omega of k lower bound. And this is for a 3CNF formula. So we're not using, k is not the width of the formula. This is important. Again, if you believe, if you run all of this proof over again and now pretend in your head that A is a monomial instead, you'll get the same result for polynomial calculus. And then you need a pigeon degree lower bound. As I said, if you don't care about the constants, then you can use our functional pigeonhole principle lower bound and you'll be fine. That's it. So then what did we learn? We learned that the Ben-Sasson and Wigderson style upper bound is tight, at least in the sense that the refutation width and the refutation degree can be square root number of variables without anything happening. But it's not exactly tight because Ben-Sasson and Wigderson says, in fact, that the refutation width can be square root n log n, and we're missing that final square root log n, but except for that, we're tight. And we also see that up to fairly small, I mean, it's interesting if you're really chasing the constant factors in the exponent, then we don't know this. But again, it's somewhere, I think for a solution from memory for 3CNF formulas, I think it's somewhere between n to the k and n to the k over 4, something like this. I erased the upper bound lemma, but again, the upper bound I think is k to the k times n to the k. So that is like the right n to the k with actually the exponent is k. And I think if you really squeeze the juice out of this lower bound, you get something like n to the k over 4. Okay. So you could still ask for it to improve, but there's not too much left. Good. Questions on this before we call it a day? Let's call it a day.